So the Gauss elimination is a good method to solve the large number of equations, but there are some pitfalls or disadvantages of this method. The first one is division by zero. One coefficient may be very close to zero or zero, and dividing by that will be a problem. So usually the pivot or the first element can have this issue. Round-off errors, you saw from the previous example that there are many numbers that we need to use to be able to eliminate the round-off error. And if we have a limited number of significant figures, then we will have issues. Important for high number of equations. A rough rule of thumb is 100 or more equations actually. Less than that will be okay. Ill-conditioned systems. Small changes in the coefficients will lead to large changes in the results. And if there is such a system, then that means ill-conditioned. And if round-off errors exist especially, it means small changes in the coefficients, because round-off error exists in coefficients. And these small errors will result in large changes in the results, and which will create some unexpected results. So if the system is ill-conditioned, if the determinant of the system is near zero, so we can simply understand this issue, this large change with small coefficient changes, which is called ill-conditioned, by first calculating the determinant of the system. If it is near zero, that means we will have such an issue of ill-conditioned systems. But the magnitude of coefficients can have a scale effect on the determinant, so we need to be careful. Instead of directly using determinant, we can simply normalize the coefficients of the equations such that the maximum one in any row is equal to 1. Then we can calculate determinant to see if it is near zero. So there is also singular systems, which means when two or more equations are identical, we can have singular systems. So we lose one equation in this case. That's a problem because we will have less equations than the unknowns. After elimination step, calculate the determinant as the product of diagonal elements. We will show this in the next slide. If a zero diagonal element is created during the elimination, it is a singularity problem. So we will have singular systems in this case. Basically, after the elimination, so we will have upper triangle, then we can calculate the determinant as the product of diagonal systems. Here, if from this we can understand what's going on if we have a singularity problem or not. Let's see this in the next slide. As we mentioned in the previous slide, the determinant is important to understand the system condition, whether if it is ill-conditioned or it has singularity problem. But for large sets of equations, determinant calculation is also a problem. It's impractical. And a Gauss elimination provides a simple way to do this. Simply we will have the first forward elimination step. Then we will have a triangular matrix. Then the product of diagonal elements will give us a determinant value. Basically, these are the diagonal elements on the upper triangular matrix. So you can see here, this is the upper triangular matrix, for instance, after the forward elimination of Gauss elimination. Then we calculate the determinant as the multiplication of these first elements, let's say. Here you can see. And a modified version of this for partial pivoting can be this value, again these results, but we will have n minus 1 to the power p. And in here, p is the number of times the rows are pivoted. Pivoting will be explained in the next slide. So let's go to the next slide and see what pivoting means. In this slide, we will see pivoting for Gauss elimination. Basically, if the coefficient of the pivot or the first element is 0, then division by 0 will occur. If the coefficient is near 0, then the system is ill-conditioned, or there will be round-off errors which will occur. To solve these issues, we actually apply pivoting strategy during the forward elimination step at each row of the sets of the equations. What we mean by this is that, so we have two pivoting actually, partial pivoting and complete pivoting. Let's see the partial pivoting. We determine the largest coefficient in the column below the pivot element. Also, the complete pivoting determines the largest element for both columns and rows. Basically, in the first one, we will have we compare the coefficients in the column and determine the largest one. In the complete one, we check all the columns and rows and determine the largest one. So complete pivoting usually not used because switching columns changes the order of the axis and consequently adds significant and usually unjustified complexity to the computer program. Basically, partial pivoting is preferred, and aside from avoiding division by zero, pivoting also minimizes round of error. As such, it also serves as a partial remedy for ill conditioning. Simply, we will check the column, basically all the coefficients in a column, or for the same unknown, let's say, determine the largest one and put it to the first equation. I mean, when we find the largest coefficient, that equation will be the first equation, so that we will change the pivot equation simply. That's called partial pivoting. In this slide, we will solve an example to understand partial pivoting. Here, for instance, we have two sets of equations, and you can see that the first equation here, for instance, have the first constant coefficient value actually is very close to zero. So that means it can have an ill-conditioned issue. So then we can eliminate this by using partial pivoting. So the first pivot element is very close to zero, and then repeat the computation but partial pivot by reversing the order of the equation. So what we want is we checked the first column. First column is this, so the coefficients of the first unknown actually. You see that the second one has a larger coefficient. So we simply move this as the first equation. So this means partial pivoting. Then simply we will have the equation order changed as this: 1x1 plus 1x2 equals 1, and 0.0003x1 plus 3x2 equals 2.0001. So now instead of solving this, we will solve this order. And in this order, what we need to do is simply multiply the first one as 0.0003 divided by 1 and subtract this from the second one. If we do this, 0.0003 x1 plus 0.0003 x2 is equivalent to 0.0003. And if we subtract this from the second one, subtract from second, then we will see that we eliminate these, and we will have an equation with only x2 by subtracting these as well. I will not write these, but from here we will find x2 as 2 divided by 3. Sorry, like this. Then we put this into here, then x1 is equivalent to 1 minus 2 divided by 3 divided by 1 actually, which gives us 1 divided by 3. So we obtain these. So this is easy when we use pivoting and changing the first equation as the equation which gives us the largest first column value. So we can apply this pivoting in the during the elimination step after each elimination, for instance, because if for example we have more than two equations, now the second equations will be compared after eliminating the first unknown. The second unknown's coefficients will be evaluated and the largest will be moved to the beginning. So this is the case. Also, let's check what would happen if we just use these as the solution. So if we start with this to the solution, for instance, what we needed to do was we simply multiply this by 1 divided by 0.0003, which gives us x1, 1x1, let's say, plus 3 divided by 0.0003 x2 and equivalent to 2.0001 divided by 0.0003. So here you can see these divisions will bring very large values, and we subtract this from second equation. Here we will have minus 9999 x2 is equivalent to minus 6666, and here we will have x2 as again 2 divided by 3. This is fine, like the same, no problem, but the values are too large, so this can be a problem. And if we substitute this into the first equation, then x1 is 2.0001 minus 3 divided by 3 divided by 0.0003. I mean, we find the same result maybe, but because of the subtractive cancellations here with very large numbers here and very small divisions, numbers of divisions, the result is very significant to these significant values. If we forget one of these will be affected too much because these are too large. Let's say we forget about this, it will be affected by this value or these ones. So the large values here will be a problem for calculations, creates a sensitivity. So that's an issue. That's why it's good to have a partial pivoting and just use this, and it's very simple to have this result, to calculate the results from this after partial pivoting. To be able to understand in a better way about this sensitivity for the significant figures, for this example, we made a comparison of naive Gauss elimination without pivoting and with pivoting. So let's say we use only 3 significant figures, then the results are these. If we use 4, the results are these. 5, you can see the results are changing, and x1 especially, you can see it's changing from here to here, and the error for the actual compared to the actual value is, as you can see, changing. Increasing the significant figure decreases the error, but if we use less significant figures, the results you can see is too large. The error is too large. But if we use pivoting, then even with 3 significant figures, we will have a very small error. So the errors are low when we use pivoting. You can see the results are almost like consistent. But here in the 3 and 4 significant figures, there is very large errors actually. So errors are low when we use pivoting in the Gauss elimination, and that's why pivoting strategy is more satisfactory, or like it is strongly recommended to apply pivoting during the Gauss elimination. So basically what you need to do is you just simply check the column of the first unknown, for instance, identify the largest coefficient and move that equation as the first equation, then perform elimination. Then for the second unknowns, check the columns, check the largest coefficient and move that as the second equation, then perform the elimination. That's simply the partial pivoting.